Yep, we can start, I guess. So today we will be talking about energy-based models again. And in particular, we will focus on self-supervised learning, how it's done, and on contrastive methods, and on regularized latent variable models. Well, so the lecture, Jan started this lecture with a brief recap of what we considered previously. So what is self-supervised learning? Like in general, it would be kind of learning when we construct both inputs and targets from the data points we have. And there are multiple ways we can do it. We can like try to predict future from the past, masked from visible, and like occluded parts from available parts. And each of these methods you can like make up how you can generate input target pairs from data points. That's the way to do self-supervised learning. Yeah, and yeah, we don't really need to know always what is like known and what is unknown for this to work. And energy-based model is like any kind of model which approximates the energy function, and it should assign a low energy to all the points on the data manifold and high energy everywhere else. And how do we do inference on these models? We basically want to minimize the free energy, this f of xi, minimize with respect to y, right? And so this is the inference for energy-based models. And in this case, we can view this energy function as a compatibility measure between x and y. And when the returned value is low, then x is compatible with y, and vice versa. And if it's high, it's not compatible. And like similar formulation we can get for unconditional models. In this case, this energy function f of y would be a measure of like consistency of the data point, like we get a compatibility between the components of y. Yeah, so here on the data manifold we have low energy, which means this data points are like look like they are sampled from our data distribution, and points over here, for example, would look improbable to our model as they have high energy, right? And one of the problems here might be that like in some cases, let's have a look here. For certain x, we can have multiple values of y, right? And this can cause some troubles when half of the time model tries to predict this value of y for this x, and half of the time this value of y. And in this case, we will have we are not guaranteed to have a high energy here, right? And to eliminate this issue, and basically to allow multiple predictions, we can use a latent variable. And in this case, the inference would be like we will first minimize the energy with respect to z, and we will get this free energy, which would be minimum of the energy function with respect to z, and this is kind of equivalent formulation. Instead of minimizing this e of xyz with respect to y, we can marginalize this expression with respect to z when beta tends to infinity, right? As you recall from previous lecture. And yeah, similar is true for unconditional case, except we don't have x in this unconditional scenario. We will only have y and z. Yeah. And okay, so that was inference. And now to training energy-based model. Basically, so at inference, we wanted to get the y, which minimizes this f of xy. And now we want to learn the parameters of this f of xy, right? And how is it done? It's we basically want to shape our energy function in such a way that it assigns low energy to the data points and high energy everywhere else. Yeah. And also we want to have this energy function smooth, right? So that we don't have a jump. If we get some data point which we did not observe during training, but it is close to data manifold, we want it to have a low energy, although we haven't observed this particular data point, right? So that should make sense. And there are like two families of methods to train, to find this parameterization of energy function. Those are contrastive methods and architectural methods. And basically, the contrastive methods are like different we try to find the points which are on data manifold and push the energy function down for that point and push it up everywhere else. And there are like several categories of these contrastive methods, and one would be max likelihood. But in most cases, this will not be tractable, and there are ways to approximate this non-tractable max likelihood criteria, and you can use different methods for that, like Monte Carlo sampling, use contrastive divergence, and in particular we will consider this metric learning methods, which are quite popular now, and noise contrastive estimation methods. Yeah. And yeah, another class of contrastive methods is would be like denoising autoencoders and masked autoencoders, which are particularly popular in language modeling. So BERT is trained using this masked language objective, right? And another like family of this training methods is architectural training methods, and they also can be like sub-classified into several categories, and we have this we can construct our learning method in such a way that we limit the possible volume of low energy, and that would be like PCA, Kmeans, and Gaussian mixture models, square regularize component analysis, stuff like that. Another way to regularize is to regularize this measure of space that has low volume, and here we consider like regularization of the latent variable, and those would be variational autoencoders and sparse autoencoders. We will also look at the details of that today. And there are also other architectural methods like contracting autoencoders, saturating autoencoders, and this score matching. But those are not the focus of this lecture. And yeah, so first let's like take a look at a very simple example. We can formulate K-means as an energy-based model. And in this case, our energy would be like the L2 norm of the difference between the y and wz, where z is one hot vector. So it's like we index into this W matrix when we do K-means, and we find z's which correspond to the closest points to y from the training data, and we find this z by exhaustive search, right? So when we do K-means, we want to find the closest closest data points from the training set to the data point for which we want to do the inference, and in such a way, the low energy space will be limited by like k closest prototypes, right? So that's like one simple way to think about this K-means algorithm. And next, we move to the, yeah.
If you jump back to the previous figure.
Sure.
So if you follow that spiral down there,
yeah.
Is it that in between those data points, you have like a good black section and then you suddenly see a white section? So is that like alternating between low energy, high energy, low energy, high energy?
So this like lines here?
Right. Yeah.
Yeah, I guess it's because we have K-means here. Here we can observe some kind of like fragmentation of the low energy space. Probably our like training set had less representatives here, or I don't know what K was used to generate this image, right? So maybe we have like so you can imagine if we set K to 1, and here is a data point, and here is data point, here is data point, here is data point, here is data point, and in this case it would be like that, right?
Right. Okay.
We will have this higher energies in between the data points.
Yeah. So what you see is that you don't have the manifold quite right because of your sampling. You have a limited number of samples, so in between the samples you have to push the energy up because you don't know. You know, even if in fact it would be on the manifold, but you don't have samples there, you still have to push the energy up. And that's why you have those white bands in between. But if you sample it well enough, then those then the known points will be close enough together so that the little white ridges won't go too far up, if that makes sense.
Right. Yeah. Okay. So that's same as that center spiral that you're kind of pointing out, that white energy, that high energy in between
Yeah.
the parts. Okay. Okay. Makes sense.
So to make K-means like work better, right? We want to have when the K-means works best, like when we have a very dense sample of the data points and when the K is high. But that will also like increase the computational cost of inference.
Yeah. Cool. Yeah, makes sense. Thanks.
Yeah. All right. So now we can move to some like one topic which has had some attention recently, and this is contrastive learning. And here you can see like an example of a contrastive learning. So we have X and Y, and in this case, X is the original image shown here, and Y can be either an augmented version of the original image or an entirely different image, right? And in this case, we compute the representations for both X and Y, and then we compare these representations, and we want to like minimize this criterion based on these two representations in such a way that similarity between these two, like original and augmented version, is high, and similarity between original version and negative sample is low, right? And there are a number of like approaches to this, and there is like progressive success in applying this contrastive methods recently. So one is this Moko paper, and yeah, so they got some reasonably good result, and Moko stands for momentum contrast, and in this case we like keep two models. One for we generate this what they call a query sample. And yeah, let's have a look at here. So one would be this online model, and another one would be updated with with momentum, like term, like exponentially moving average of the weights of the online model. And in this way, they keep like a number of samples produced by this like momentum model predictor in a query, and yeah, that's one way to make it work. And yeah, but the results were not so good compared to this Perl, which is the next one. And Perl used this noise contrastive estimator criterion, and I think it wasn't introduced here, just they used it successfully to train this kind of models. So here you can see that we have two heads, and yeah, so we use a cosine similarity as a similarity measure. And you can see that here is a temperature parameter. And this is like softmax-like function, this h here. And we have here original image and transformed image, and similarity between those two, and normalized by this again, this is the same component, and also this is the sum over negative samples, right? So here you can see a sum of exponents, so the similarity measure of the transformed image and with all the negative samples. And the total loss would be negative log of this function evaluated for the original image and transformed image, and minus the sum of like 1 minus this function evaluated for all the negative samples. So this function, it's like a softmax, it's bounded between 0 and 1. So basically, to minimize this total loss, we are trying to maximize this one, and so we try to maximize this one and minimize we want this component to be low. So we want to have like 0 everywhere for this evaluation and 1 for this evaluation, right? We want to have 1 for the same image and its transformed version, and 0 for negative samples for value of this function. Okay, and here are some results of this Perl algorithm like applied, and they have some. These are the scores using like 1% of labeled data and 10% of labeled data. So those are pretty good, but the results produced by the next take on that, which is SimClear framework, are even much better. And here you can see like top 5 accuracy for this SimClear model trained on 1 and 10% of the labeled data, and the scores are pretty good. And yeah, same for top 1 scores. So we can have a brief look on the takeout from this SimClear paper. Here on the right, you can see like their block scheme of their model, right? So they from the original data point, we produce 2 transformed versions. Then we compute. Here you can see that encoder, this f function, is like the same here, and then we this g would be a projection. So we don't measure the similarity on the hidden representations we want to learn. We do another we have another projection layer, and they found that to be useful for this kind of models, and this can be nonlinear projection. It works best when this g function is nonlinear projection. And yeah, so like key points from SimClear paper. So compositional of multiple data augmentation operations is crucial in defining the contrastive prediction tasks that yield effective representations. In addition, unsupervised contrastive learning benefits from stronger data augmentation than supervised learning. So here that they used like really heavy augmentations on the data. And yeah, introduction of nonlinear transformation between the representation and contrastive loss substantially improves the quality of learned representations. So it kind of like releases some restriction of how this learned representation can be, right? Because we actually measure the contrastive loss on another, like this would be a simple projection, nonlinear projection layer here, but it allows to probably learn for the model to learn some better representation, right? And representation learning with contrastive cross-entropy loss benefits from normalized embeddings and an appropriately adjusted temperature parameter. And this basically, like, they found that that kind of loss function, noise contrastive estimation, we considered before, works good for this kind of models. And they compared like 3 objective functions and found that that one works good. And
sorry, the H would be the output, let's say, from like a global average pool. That would be the last layer.
So yeah, like this is an output of the, like, in case of this vision applications, it would be output of convolutional encoder of ResNet 50, right?
Right. So I'm saying like ResNet 50, but you would lop off the like the final linear layer, right?
They have like here we can just briefly check. Let me find this comparison of. Yeah, so it will be this 2048 dimensional vector, right?
Okay.
So they have here only one data point. Here they show that the projection is useful for this kind of tasks. Okay. And they compare linear projection, nonlinear projection, and no projection. So that would be using H directly, that which is 2048 dimensional vector outputted by ResNet.
Good. Yeah, sounds good.
So yeah, here you can see like this 3 losses they compared, and this is normalized temperature cross entropy, and it's pretty much what we saw from that Pearl paper. And yeah,
the negative crosses thing seems to be like the similar to what Word2Vec used for the estimation, at least, you know, because they were again comparing a large vocabulary, so they wanted similarity to go up and then the non-similar words to go down, if I recall correctly.
Yeah, sure. I think that, yeah, they used something very, very similar to that, right? And also they had some this problem with negative sampling, right? When they trained the model, they tried to like do this negative sampling efficiently somehow, if I recall it.
Yeah, that's
correctly.
what it at least made me want to go back and look at that and compare.
Yeah, but that's basically very very popular kind of loss function for many tasks. So basically maximize similarity between U and V plus, which are like produced from the same data point. And also we have this temperature factor here, which was found to be useful, I think, empirically. And while minimizing the similarity between negative, the U and V, which are negative samples here. So yeah, basically we have also here a positive sample included. So in this case, it would be like we push energy up everywhere, and then we push energy down on the positive sample. Okay, so back to the slides. Yeah, so this seem clear results. And yeah, so Jan said something like he thinks that this SimClear approach is something very close to the limit of contrastive methods, because like they had a giant amount of compute and very large amount of data. And we can also check some papers which came out after this lecture was done. So there was a SimClear 2 released, which basically showed that this unsupervised contrastive or self-supervised contrastive learning benefits greatly from making the models very large. And yeah, so, and also they showed like alternative, yeah, that's not this one, here it is, okay, I don't have it. Yeah, they showed like how you can best leverage this kind of pre-trained models. Yeah, so here you can see that they use a couple of projections and then trim the last two layers, these projection layers, and again, yeah, and this scheme shows how you can best leverage this pre-trained model, which is obtained in self-supervised fashion. So they first do this, we can say like unsupervised or self-supervised pre-training. Then we do supervised fine-tuning. We have some amount of labeled data, and it is much smaller than amount of unlabeled data. We fine-tune this pre-trained model. And then we do the third stage, which is called self-training / distillation. So we can take either smaller or the model of the same size as we pre-trained. And then we use the scores this model, this fine-tuned model produce for all the data we have, or like a large part of the unlabeled data. And we use the scores as an object, like as a target for training this distilled or just a self-trained version of a model. And they found this teacher-student approach useful here. And yeah, so that's interesting. Okay, and another recent advance in self-supervised learning is from this bootstrap your own latent paper from DeepMind. And what they did, let me show you their training approach. So here we have this image, and we have two distinct models here, which are very similar. And the difference is this model has its weights like updated with exponentially. This is an online model, and this is exponentially moving average weights model. And we compute this, we augment the data point, and then we compute the representation here. Then we apply a projection to it to obtain like this z, which would be kind of hidden variable, which we will, then we apply another like simple function to it. And we try, here we don't apply any function, right? So we try to predict this augmented z produced by this exponentially moving average variant of a model. We try to predict it from the output of the slightly different online model. And yeah, so we basically, this Q is is a function which is supposed to negate the augmentations applied to t, right? So what is the difference between z xi and z theta? The difference is like a small difference between weights of these two models and difference between augmentation. So the augmentation shouldn't introduce like semantic difference. They just introduce some difference which we expect to be not meaningful for learning useful representation, right? And somehow and as you can see here we don't have any negative samples, right? And that's really surprising and cool that this works, because if we don't have negative samples, we can have very simple solution to this problem where our representation is just constant, right? So we have some constant vector here, and then we will always have like zero difference between augmented version and original version, because it does not depend on the augmentation, because it's constant. But somehow they manage, probably because of this exponentially moving average and like smart augmentations, and maybe like smart training dynamics, they manage to make this work. So that's kind of cool. So yeah, and the latest paper from Facebook, maybe not the latest, like this is the latest approach to training this self-supervised models, is it's called SWOW. I don't know how it's pronounced properly, but here again we don't have negative samples, and let's compare. This is like regular kind of contrastive learning, and so what they try during training, for each sample, they assign each sample is assigned to a cluster, and we try to predict a cluster from for one augmented version from another augmented version, and vice versa. And in this way, we obtain the codes, and yeah, so we want to both augmented versions to be assigned to the same cluster, right? And again, in such way, we can do this semi-supervised training without negative samples. And yeah, so why is this important? Because obtaining these negative samples has like two problems. First, it's very computationally expensive, right? We need to compute a lot of like similarity matrices on bunch of samples. And another, we need to obtain this negative samples, which would be representative of the overall data distribution. And that's not an easy task, because we need to make these negative samples somehow meaningful. Because for that example we had before here, it's probably very easy to learn to distinguish between, to assign high similarity to these two and low similarity to these two, right? So we need to have this to obtain these negative samples, which would be useful for learning their meaningful representations. Okay. And yeah, so this latest advances in contrastive methods allow to train without negative samples. So that's pretty cool. Okay, next, another self-supervised approach is denoising training. Like we have our data point, we corrupt it, then we predict we do prediction on the corrupted version, and then we want to like reconstruct the original from the corrupted one. And this works great in text applications, but it works not so great with vision applications, because the output space for image is very high dimensional, right? So we have like either like infinite continuous output space, or even if you like quantize an image, right? You can quantize it theoretically, but it would still result in a combinatorially large number of possible patches here, right? So that's why this denoising autoencoding, which works so great for natural language, it's not so popular for other applications where it's more difficult to like reconstruct the original from the corrupted in like consistent way. Okay, so, and here is an example of application of this denoising objective. And here you see the spiral here, and this is this bright points are on the data manifold, and these orange points are noisy data points. And here is this energy function learned for this data, and you can see this area of low energy here, and it results from this ambiguous reconstruction. We, for each point which is like here, we can either reconstruct it to be on to be here or to end up here, right? And the same is true for image, but like in more complicated way. Basically, for any image, there is like infinite or combinatorial number of ways you can fill in patches here. All right, and there are like other contrastive methods, and Jan mentions here the contrastive divergence and persistent contrastive divergence, which are used mostly to train RBMs, restricted Boltzmann machines. And yeah, for restricted Boltzmann machines, the energy may be given like this, right? But and this contrastive divergence is kind of a way to train it, given the fact that it's hard to estimate normalizing factor for minimizing this energy, because we have a lot of data points and we want to normalize each of this negative log likelihoods by their average energy, right? So something like that. But yeah, RBMs are not so popular nowadays, and I can probably move on to the next topic, right? And the next topic is regularized latent variable energy-based models. And this is a topic Jan LeCun is particularly interested in now, and and he says that limiting the information capacity of latent variable z might be one of the most important like goals for deep learning nowadays. And why is that? So this introduction of latent variable basically allow us to learn multiple like one-to-multiple mapping for x and y pairs, and we have this a data manifold, and like not a manifold, like a manifold we have for each input, and we can, when varying z, we can move through that data manifold. And yeah, and why do we need to limit this information capacity of variable z? Because if we have large enough z, we can reconstruct perfectly any y from just z, and this will result in like constant energy function everywhere. So the energy function value will be constant because to obtain this f of xy, we minimize e over z, and if z is like unrestricted, we can always like produce a low energy for each. We can find minimal energy for each data point, right? And what are the ways to regularize z? So we add this to our energy function. We add this regularization term, which depends on z, and one way to limit the information capacity of z would be to, if we know the effective dimension of z, we can restrict z to be of that dimension. And he gives that example that probably degrees of freedom of human face is bounded by a number of muscles we have, face muscles, and we know a number of these muscles. So the number of degrees of freedom would be approximately equal to 50, and it makes it like reasonable to set the dimension of z to be 50. But that's all great, but the problem here is we don't usually know underlying number of degrees of freedom for our data distribution, right? And to do something similar, we can try to use this L0 norm, which is limit the number of non-zero components. Or more practically, we can apply L1 regularization to z, and it will result in a sparse z vector. And other ways, important and popular way to restrict the information capacity of z is add noise. So we instead of having deterministic z, we sample from some distribution of possible z's, and also we limit L2 norm of this of z, and this results in variational autoencoder, which we will consider later. Okay, so the task here would be given this h and z regularized version of it. We want to, the training objective would be like minimize the difference between y and y hat while regularizing z. So, and like we can consider an unconditional case when we don't have any x here, but we want just to train a sparse autoencoder. And in this case, we apply L1 regularization to z, and our energy will be the difference between y and wz, which is this term here, and absolute value of z, which is this regularization term here. And effectively, it would be like a piecewise approximation to the data manifold shown here. But he also mentions that this particular picture is not produced from real actual from this model. Yeah, so that's just something similar to it. But here you can see, like as we will have to switch between sparse z's, and we have this like piecewise linear function here, like superposition of piecewise linear functions. Okay, so again, what is the problem here is that for inference, we need to minimize this energy function, this energy function over z, and this is not an like super easy task. This is basically a popular problem in or known problem in convex optimization, and there is an algorithm called ISTA. Probably we will have, yeah. So we have here this algorithm called ISTA, which is an iterative algorithm to compute, to minimize that E function over Z, and it's done. It's done in, like, we do k steps, computing like Z for t+1 step from Z t step, and shrinkage function is this function. It would be like, and it corresponds to minimizing the regularization term, and gradient update would be like responsible for keeping it close to the gradient of this C term here, which is differentiable. And so what is an interesting thing here, like you can see that this iterative FISTA algorithm is kind of similar to recurrent neural net. And what people tried, they tried to like learn an encoder which will try to predict z, a sparse z, which minimizes that energy function in the same way, like we do k iterations here, and basically they managed to obtain much better results with this learned ISTA approach as compared to original ISTA FISTA approach, and this Lista encoder, it is trained to, like, at training time, it is trained on these, which are obtained by this classical optimization. But on practice, and then when we have it trained, it produces like much faster convergence for this kind of problems. And there is another, like, you can search for trainable ISTA, and that is an improvement over learning ISTA, like another improvement. So that is pretty interesting, that we can like obtain this learned approximation to this algorithm which minimizes Z, which converges much faster than like analytically derived algorithms. Okay. And yeah, so here they showed a bunch of results they have that there is another variant of Lista, learning coordinate descent, and it's even better. And yeah, so basically this is pretty cool demonstration of the applications of learned functions, right? So it's pretty interesting. And here are some results of application of this sparse autoencoder approach. And here they obtained 256 basis functions. And we can take a linear combination of this small number of these bases to reconstruct any number in MNIST. And that's pretty cool. And the same algorithm is applied to like CIFAR, and yeah, so animation was supposed to be here, but it's not. And yeah, but here you can see that these are learned filters, and they are very similar to those like filters which humans have in their brain, right? So this kind of like simple edge detectors, it's very similar. So with this sparse sparse coding approach, we get filters which are very similar to those found in human brains. That's pretty interesting. And yeah, so here they show like bunch of filters learned when we vary number of filters in the encoder and decoder. And you can see that like those filters are very kind of similar here. So we learn like I mean, similar filters are learned by encoder and decoder, and we learn to like undo the encoding in decoder. So that's also pretty interesting. And
is there any like meaning with as the number of filters are increased, like you're seeing different things, right? Is there anything there to that part? That one, two, four.
I'm not sure about this, so he didn't like focus on this in the lecture, and I think that basically how can we interpret this? That as number of filters increase, we learn more and more meaningful features. And in this way, we like find some reasonable dimensionality of Z we want to have, right? So if we have a single filter, we have this, like, you see this basically something kind of like Gaussian filter, right? And as we increase number of filters, we start to learn these edge detectors. So yeah, if anyone has something to add on that, maybe read this paper or have some experience with sparse convolutional autoencoders, yeah, so feel free to jump in and enlighten us.
With the one filter thing, the two takes that I wanted to wonder which makes most sense is that like obviously I think that's the most important filter that it can understand if you just provide it with one filter on encoder and decoder. But at the same time, does that one filter kind of average out all the things that is there? That's why you kind of see like just a blob there. And then, because that theory kind of holds if you look at 1, 2, 3, 4, and then there you don't see that there is nothing circular there in the 4 scenario, right? I mean 8 scenario. In the 16 also you barely see a circular scenario, but then it again pops back up to 64. So yeah, I was just kind of curious, like if someone has some idea what it means, if there is anything there to it.
Could it be like an attention map? You know, so when you have just one filter, is basically saying, look at the center, right? And when it has, you know, as the number of filters go more and more, it says, okay, look at these features, and this will help you make the classification, right? So that was the intuition I kind of got from there. But,
Cool.
Yeah, I think might make sense that if we are very limited at what we can look at, we just try to like look at the center, right? Yeah, and here are some examples of sparse codes from the encoder trained on CIFAR10. And yeah, and the filters learned. So you can see here, when you train on CIFAR10, you get a bunch of edge detectors and also some filters which will respond to the particular color, right? Looks like looks like that. All right, so that's sparse autoencoders, and another variant of autoencoders, variational autoencoders, and we will have like a preview here, and we will have another like practical session next week on it, and we will go into the implementation details. So here is the idea behind variational autoencoder. So instead of minimizing our, instead of taking the minima Z for energy, we sample from some distribution. And yeah, so the encoder here will produce the parameterization of distribution from which we will sample Z, and then we use this, we feed this like perturbed or like randomized version of Z. We feed it to the decoder to obtain the reconstruction, right? So we encode Z. We encode this Y here, and we get the parameters of the distribution based on the data point we observe. And then we use that like sample from a distribution parameterized by which mean and variance depends on y here, is dependent on y, and then we use it to reconstruct y. Okay, so and here you can see we will consider step by step how it works. So we get some numbers here, which are the outputs of the encoder, and yeah, so actually outputs of the encoder would be like means and variances for z here, and then we sample each like data point. Will instead of like providing a single point z here, we will like sample from this bulb here. And you can see that because we sample here, this bulb can overlap, right? And when the bulbs overlap, we have a bad reconstruction, because so we want to have different reconstructions for these two data points, but because for example our z can we can sample z which will correspond to this data point here, it will be probably reconstructed to this one, right? And this will obviously have a high loss value. And so what the model will try to do, it will try to push all these different points away from each other, and in this way we will again get a good reconstruction, but not a meaningful representation. All right, so so here you can see like we can like obtain this well separated z's by like pushing these points away from each other, but that would cause that problem that we don't learn a useful energy function by doing this, and that's why we add a regularization term, and our regularization term should like effectively what is depicted here is it would be well, here it's shown like we want to have our mean to be close to 0, which is like standard normal distribution, right? So and we will this string shown here, we will have not only like regularization over means, but also regularization over variances. We want basically the regularization term pushes this mean and variance of a distribution returned by encoder towards a standard normal distribution, and this is done by applying KL divergence on this standard normal and like output of the encoder.
Arto,
yep.
So what if forcing the Gaussians to be unit normal, sorry, zero mean unit variance Gaussians? What if that's not small enough? What if they still overlap?
Yeah, so actually we want them to overlap. Like let's consider, but we want them to overlap in a meaningful way, and probably you will definitely understand the details of this after the practical session, but right now let's imagine So like this reconstruction error tries to push these points away from each other, right? And this regularization term, the KL divergence between like normal distribution and our predicted distribution, it pushes all the points towards zero mean unit variance. And in this way, the model can deviate from standard distribution only in that cases when it is useful for reconstruction, but it will not do that if the reconstruction does not change change too much, if we don't change the parameters a lot. And in this way, basically, if we, for example, if we have say we do it on mnist data set, and these 2 points are both threes, and we don't mind two outputs of the encoder for 3 to overlap, right?
Yeah.
But and this point is 8, and we want to separate 8 from 3. So in this way, basically, as you can imagine, we are supposed to learn like a meaningful, like we are supposed to pack all the possible this here in a meaningful way in a restricted area, right? So
yeah, I guess the question is that, you know, unit variance, what if unit variance balls are too fuzzy and that all the digits are overlapping? So I mean, I'm thinking, why choose unit variance? Why not learn the right value of the variance? That's just a question.
yeah, so we learn the variance. So it's not shown here. Basically, we will have another like string here, which may be, I don't know, shown like a string which will be between this boundary and a center of a point, when the like not a center of a point, but it will be like attached to like 1 here, 1 unit radius, and if we can deviate from it. So basically, like in practice, we will have this multi-dimensional variance vector, and like as well as mean can deviate from 0 if it's useful for us. Also, a variance can deviate from 0. So a variance is also outputted by encoder here. So this encoder, it outputs like a double dimension of z, and it will be used like how it's I think how it is at least one way to do it on practice. We will like sample a random variable from a normal distribution and then reparameterize it with the outputs of the encoder, and we will take half of the outputs as reparameterization for means, and half of the outputs as a reparameterization for variances. And so basically, we learn both means and variances from which to sample. And actually, I think if I'm not wrong here, I think at this practical session, what Alfonso showed, he showed like he computed z for say 3, and he showed how it can be, and z, for example, for 8, and it showed that when you interpolate between those two, you can like move from 3 to 8, and the reconstruction moves appropriately. And we have like as we move from the interpolation like as we move along this interpolation from z for 3 to z for 8, the reconstruction produced by decoder will be 3, 3, 3. Here it will be something like in between maybe, and then it switches to 8. So that would be in like ideal case, right? So yeah, so we will spend more time on variational autoencoders next week. Yeah, and that's probably all we had for this lecture. So any more questions or points to discuss?
Thanks, Argo. That was great.
No questions. Can we kind of revisit Lista, Arto?
Lista, yeah, sure. Let's go to, okay. Which slide is this one?
Yeah. I kind of missed that. Like, what is the purpose, like moving to the RNN to kind of predict? Yeah, that is the part which I kind of completely lost. I didn't understand.
Okay.
What is he trying to?
Yeah, so here, yeah, that is somewhat complicated maybe. So, or maybe not. Let's try to understand it here. So when we try to do inference on this model, we want to minimize energy function shown here. This is an energy function, and we want to minimize it over Z. And Z is a sparse, and we want to have Z sparse. So basically, Z is a latent variable, so it's not observed. We don't know Z, but to sample from to sample from this energy function, we want to first minimize E of XYZ over Z to obtain F of XY, and only then we can do variance. And minimizing this E of XYZ over Z is like convex optimization problem. And ISTA here is an algorithm which allows to solve this convex optimization problem. But yeah, and it makes sampling from like inference using this sparse predictive sparse model costly.
Okay.
And yeah, so and this idea to use RNN for minimizing over Z, we will not like minimize over Z by like interacting with this energy function. We do not solve, instead of solving this optimization problem, we will learn a function which will approximate the solution for this kind of task. And as it is, so they used RNN as it is very similar to, yeah, basically this ISTA algorithm is iterative algorithm. It kind of resembles RNN in its structure.
I see. Okay. So it's basically that the RNN is substitution for the iterative part of it.
Yeah.
And okay, I see.
In this case, we will, given Y, we will feed it to RNN, obtain a sparse code from it, and then feed this sparse code to a decoder and obtain the reconstruction. And in other case, we would have to minimize, like given Y, we would have to solve this minimization problem to obtain Z, this sparse code, right?
Okay. Cool. Okay. So with the RNNs case, you basically take time during training, but at inference, yeah, you can just spit it out because you would have probably learned all the weights in that sense. Whereas the other one, you have to still run it iteratively at inference too, right?
Yeah.
Is
Yeah.
that okay?
That's how I understand it.
Okay. Cool. Yeah. Yeah. Thanks.
Sure.
Now, one question that always occurs to me when listening to these lectures is to build the energy function is essentially a constructive operation. You have to start with only the training examples, and then you have to build an energy function that exists everywhere. And I'm just wondering if that's always possible. I mean, what if most of these techniques are, or at least the ones that I've seen, are building it from some kind of a linear, locally linear approximation. But what if this energy space has all kinds of kinks and valleys and so on, and trying to reconstruct it or trying to build it or to build it with linear approximations is going to fail. I mean, I guess the question is how do we know that it's always possible to build this energy function?
Yeah, well, I can like give my thoughts on that, and yeah, everyone is welcome to like share their thoughts. It's a really interesting question, and I think it kind of relates to the question like how deep neural networks work at all. So in this high-dimensional space, it seems like we can find we can find this kind of data manifold which will be smooth, right? Because we operate in such a high dimension, it's kind of possible to find very smooth space. On the other hand, about that, we need to find this a value for energy function everywhere. So I think that's kind of open problem, and like we don't have any guarantees that our energy function will be good everywhere. We only know that our energy function will work for the data points we observed during training, right? And that's like kind of an art, right, to construct energy function in such a way that it will generalize well. And that's why, like, as you remember, we had there like mentioned that we want to learn smooth energy functions. So we don't want them to be too kinky, right?
Yeah, so I'm kind of imagining a case where you can start building this energy function, and then you can only go so far, and then things get divergent or something, or you're not really. What I'm thinking of is like you can reconstruct part of the energy surface, but then there are parts where you can't say anything about. I'm wondering if that's something that people run into. Parts of the space that you can't really be sure that you're getting a good energy function in. I don't know. It's not very well formulated.
Isn't that the case when he gives the example of the autoencoder with images? That along with that, the output space is not discrete. And when I say discrete, I mean images are discrete, but it's like infinite total combinations. Putting both those together, you kind of don't. It kind of exactly kind of emulates what you're trying to say, right? That the space is not kind of represented well there.
Yeah, so maybe that's goes back to what he was saying earlier, that you have to work with discrete spaces with relatively low dimensions, because if the dimensions get too high, then it becomes more like a continuous space.
Too much, yeah. And there was a nice, I think, comparison that he drew somewhere, I don't know which point in the lecture, where he pulls how cross-entropy loss can be visualized as a contrastive loss too. I forgot the exact words, but somewhere in this lecture he does mention that, and I think that's a nice parallel where he talks about how you want to spike these points, which is like reducing the energy for the correct class, whereas you reduce the probability for the wrong classes, which is like spiking the energy up on those classes. So again, like if it's a discrete case, that's a lot more easier, whereas once you kind of enter this huge dimension problem with images, then it kind of becomes hard to make it a smooth loss, a smooth energy function. Sorry.
Yes, it's kind of like all that said, it's still like still surprising that all this works at all, right? Given their like possible amount of like number of possible images, it's really very big. But on the other case, like on the other hand, like we as humans, we do not even think, we don't even think of considering like the full space of possible images, right? So we have this notion of basically we have knowledge of properties of natural signals, as we talked also in this course before. So we know that images are supposed to be like kind of yeah. So there was those properties.
Like, I think he calls it compositional, the property that images have local patterns. You know that they're composed of local patterns.
Yeah.
So
yeah.
that limits the possibility, the number of total possible things that would be considered natural images.
Yeah. So we don't need to consider like the full space of possible like values for each like pixel of this image, right? So we kind of already know that it's probably not very natural if this patch will be like black, just a black rectangle, right? So we know that here probably is another, it like continues to be red, right? And here it's supposed to be something similar to what we see here. And yeah, so that's basically like the goal of constructing like engineering the learning algorithm and architecture of the neural network in such a way that it assigns like this high energies to all those points that do not make any sense, like easily, right? Because it kind of knows what is natural image and what is not. And I think it's kind of what, for example, like stands behind GANs. So when we train like this generative adversarial networks, basically at the beginning, the generator can produce some nonsense, but somehow it uses the like signal from a discriminator to figure out that you need to generate something which will look like natural image. And there is like a bunch of other considerations, like for example, that adversarial attacks you can apply on any kind of data, and which work on basically all kinds of neural networks if they are not trained with adversarial objective. That is also kind of one way. This adversarial training is another way to smoothen the loss landscape, and basically to smoothen energy function if you want, right?
Thanks, Ardo. That was really well explained for a very complex lecture. Do we have any questions before we end the meeting?
Thanks, Arto.
Yeah, sure. Thanks,
Thanks,
everyone.
Arthur.
Thanks, Ardo.
Attention.
Thank you.
Thank you.
Thanks, everyone. Goodbye.
Thank you. See you next week.